In these videos, we're going to be discussing Chapter 5, which discusses probability. First, we need to go over a couple of definitions. Probability deals with experiments that yield random long-term results or outcomes, yet reveal long-term predictability. The long-term proportion in which a certain outcome is observed is the probability of that outcome. As the number of repetitions of a probability experiment increase, the proportion in which a certain outcome is observed gets closer to the probability of that particular outcome. This is what we call the law of large numbers. In probability, an experiment is any process with uncertain results that can be repeated. The sample space, which we'll designate as the uppercase letter S, of a probability experiment is the collection of all possible outcomes. An event is any collection of outcomes from a probability experiment. There are two general rules of probability. The first general rule of probability is that the probability of any event, uppercase E, has to be greater than or equal to 0 and less than or equal to 1. So probability of any particular event will always be a number less than or equal to 1 but greater than or equal to 0. And the sum of all the probabilities of all of the outcomes must be equal to 1. A probability model lists the possible outcomes of the probability experiment and each outcome's probability. Now, if an event is impossible, then the probability of that event occurring is 0, or we could write that as 0%. If an event is certain to happen, the probability of the event is 1, or we could write that as 100%. An unusual event is an event that has a low probability of occurring, usually less than 5%, although this is not set in stone. Probabilities can be approximated using two methods, which we will demonstrate on the next page. The first is the empirical approach. The empirical approach would be used if you flipped a coin 20 times and recorded the number of heads, for example. So if I flipped a coin 20 times and let's say I got 11 heads out of 20, then the probability of the next coin being a heads is going to be 11 out of 20, which obviously is slightly more than 50%. Or we can use what's called the classical approach. The classical method calculates the probability in instances when you have equally likely outcomes, for example, flipping a coin. So in this case, flipping a coin, we know it's a 50-50 chance of getting a heads each time. But using the empirical approach, it's based on history alone. So if, based on history, I flip the coin 11 out of 20 times, well, that's going to get me to 55% on the next throw might be heads. So the empirical approach will be based off of history, where the classical method is just based on how many outcomes there are, how many possible outcomes divided by how many possibles there are. So there's 1 heads out of 2 possible outcomes, which yields 50%. These two numbers are not necessarily going to be the same, although they certainly can. And that's where the law of large numbers comes in. The law of large numbers says that as the number of repetitions of a probability experiment increase, then the proportion in which a certain outcome is observed gets closer and closer to the actual outcome. So in this example down here, if I were to have flipped this coin more than 20 times, maybe I flipped this coin closer to 100 times instead of 20, well then this probability is going to start looking more and more like the realistic or theoretical probability using the classical method. So the more I flip the coin, the larger the n becomes, the closer that the empirical probability gets closer and closer towards what classically is the theoretical probability using the law of large numbers. The empirical versus the classical method. The empirical method obtains an approximate probability of an event by actually conducting an experiment, whereas the classical method does not require an experiment actually performed. So on the next page, we're going to do an example. And in this example, we're going to be flipping 3 coins. We're going to flip all 3 coins one time, and we're going to count the number of heads that are on the 3 coins. Then we'll repeat that process 50 times and fill in the following table. But let's first list all of the possible outcomes. When I flip 3 coins, for example, it might be these 3 pennies here, and I flip all of those pennies in the air and they all land, this is one possibility. They could land all tails. So one possible outcome would be tails, tails, and another tails. I could also flip it so that it might be a tails, tails, heads. It could also be a tails, heads, tails. It could be a heads, tails, tails. And at this point, I think I'd like you to pause the video and see if you could come up with the remaining 4 outcomes. There are 4 more left, and I'd like you to pause the video and try to come up with the other 4 possible outcomes. Is this what you came up with? Well, as you're going to see in the experiment, you could come up with 3 different options. You can come up with no heads at all. So this first example would be an outcome with 0 possible heads. Or you could come up with 1 heads, which would be these 3 options here, which has 1 heads total, and it could be in the last spot, the middle, or the first spot. So there would be 3 possible outcomes that might get 1 heads total. There are 3 possible outcomes that might get 2 heads total. And then there's only 1 possibility of getting 3 heads total. So what we're going to do is we're going to flip these 3 coins, and I'll do the first simulation for you, and then I'll let you do it on your own by pausing the video. So for example, I'm going to flip these 3 coins, and I'm going to let them all land, and it looks like I got 2 heads and a tails. So I'm going to put a tally mark right here next to the 2 because I got 2 heads. Let me try it one more time. This time I got 1 heads, so I'm going to put a tally mark right there. So I'm going to let you continue this by pausing the video. I'd like you to flip your 3 coins 50 times, fill in your tallies, and then we'll continue the rest of the table together. So go ahead and pause now. Okay, so I finished flipping my coin 50 times, and I found that I got a total of 8 total flips that had 0 heads total. In other words, they were all tails. Using the empirical probability, this is based on history, I know that I would have 8 out of the 50 total that would have received a heads. Using my calculator, I find that this comes out to 0.16, which is 16%. So my probability would be 16%. Again, probability has to be a number between 0 to 1, or in percent form, 0 to 100%. Let's move on to the next one. I counted a total of 17 of 1 heads total. Using my empirical probability approach, 17 out of 50 is 0.34, which is 34%. 2 heads, I received 20. 20 out of 50 is 40%. And I received 5 all heads. 5 out of 50 is 10%. And you're going to notice as one of our features of probability is not only does each individual probability have to be a number between 0 to 1, but all of the probabilities have to add up to 1, or percentages add up to 100%. And that will always be true. So I'm going to let you go ahead, pause the video now, and finish the rest of this table. Clearly your table is not going to necessarily match mine because you flipped your coins in a different distribution pattern than mine. So pause the video and finish the rest of this table, and we'll come back and do the right side together. Okay, now that you're back, the classical probability, these numbers were all going to match because these were based on history, which all of us might have had different numbers. But classical probability, all of our information will match. The classical probability is using what's called the law of large numbers. If I were to flip this coin, let's say 1,000,000 times, this 16% is going to get closer and closer and closer to some theoretical value. It's going to converge into some value. Since I know how many possible outcomes there are, which are 8, out of those 8 possible outcomes, how many of these outcomes are 0 heads? This is the only one that is 0 heads. So there's 1 out of 8 possible outcomes that might achieve that 0 heads, which is all tails. A 1 out of 8 is a 0.125, which is 12.5%. And you can see that these numbers are close, and that's going to be likely that those numbers will be close, especially if your sample size is fairly large, and 50 is a decent sized sample. Clearly we could utilize more, and the more we would have a larger sample, the closer that the 16% is going to start to look more and more like the theoretical probability or classical probability, which is actually 12%. So what do you think the percent would be for 1 heads total? Well, how many out of these 8 possible outcomes have 1 and exactly 1 heads? Well, you can see that there are 3 possible outcomes. 3 possible outcomes out of 8 is 37.5%. 2 heads, there are 1, 2, 3 possibilities as well out of 8. So I'm going to get the same probability for this one. And for the last one, there's only one way to get all heads out of 8, which again is going to be 12.5%. And I know that I did this right because when I add all of these numbers together, I get a total probability of all possible outcomes of 100%. So you can see our distribution is not too far off. You can see I definitely have less at the beginning and at the end and more in the middle. Same with our distribution, that would be over here. But it asks, did our empirical probability equal the classical probability? And the answer is no. Okay? And it asks, why not? And what could I do to better align these values? Well, the reason is no is because our sample certainly does not equal the total population. And the total population would be all pennies in the world being flipped or infinite number of times. Clearly, any sample is always going to be a poorer representation of the population, but the larger your sample is, the better the representation of what the population actually might be. If we took a bigger sample, for example, we would get closer to the classical method, or the empirical probability would start to get closer to the classical probability. So let's do one more example. This time we're going to need dice. So what we're going to do is roll 1 die, and we're going to record the number of pips that lie face up. Pips are the dots on a die. Each of these dots are called a pip. And so we're going to roll this one die and record the number of pips. So whether it be a 1, 2, 3, 4, 5, or a 6, or 6 possible outcomes. So obviously our 6 outcomes, you can get 1, 2, 3, 4, 5, or 6. You could have simply just put the numbers in there too. Anyway, so our possible outcomes are the 6 sides of the die. So we're going to repeat this process 50 times. So let me do the first 2 for you. So I'm going to roll my die, and I rolled a 5, and I'm going to put a tally next to the 5. Then I'm going to try it again. Oh, I got another 5. So I'll put another tally mark there. So I'm going to repeat this process again 50 times, just like we did in the above example with the coins. This time I'd like you to fill in all of the tallies, all 50 frequencies, and then go ahead and see if you can figure out what the empirical classical probability is going to be and complete the complete table. Pause the video here, and then we'll come back and see how similar our numbers were. Okay, so I finished my experiment, and obviously your numbers over here using the empirical method are probably not going to match what I have. I went ahead and rolled my die 50 times, and I got this distribution of each of the numbers, which theoretically we know they all should be equally likely, but in reality that doesn't necessarily happen. The empirical probability, I received 11 out of 50 rolls that received a 1 pip on the die, which is a 22%. 2 pips, I rolled 5 of those out of 50, which is 10%. And so on and so forth. You can see that all of these total 100%. Now the classical probability, we will all have the same information. Classical probability takes the number of possible outcomes, which is 6, and in the numerator, how many outcomes are likely to happen. We want only 1 to occur. There's 1 side out of 6 sides of the die, which is a 16.7% chance rounded that I might roll a 1. Since the sides are all equally likely, as long as the dice is fair, then we will have a 16.7% chance of all of those sides occurring being equally likely, which adds up to about 100%. In the next section, we're going to be discussing section 5.2, which is the addition rule and complements. So let's first discuss the probability of more than one event happening at the same time. 2 events are considered disjoint if they have no outcomes in common, or in other words, we also call this mutually exclusive. So I'm going to go ahead down here and I'm going to start drawing some pictures now and then come back to these results in just a moment. Okay? So first let's draw what's called disjoint, or we call these mutually exclusive events. Okay? 2 events are considered disjoint. So event E and event F are considered mutually exclusive if they do not share any people or objects in common. An example of this would be the grade of an A versus the grade of a B. So in this particular statistics class, for example, whether you get an A or a B are mutually exclusive because they cannot be joined. There's no common ground in the middle. Nobody can earn an A and a B at the same time. You either earned an A overall or you got a B. Not disjoint some people might call them joined, simply just means that they do have objects in common. An example of this would be, okay, everybody in the E group is in statistics. Everybody in the F group is taking advanced physiology. There might be some students that are in here that are taking both classes at the same time, and that is possible. So that's an example of objects that would be disjoint. Okay, so let's go back to the rules now that we know what the difference between mutually exclusive and not disjoint are. And this says that the addition rule for disjoint events, it says that E and F are disjoint events, then the probability of E or F occurring is simply just the probability of the two independent events added together. So again, if I come back down here, if they're mutually exclusive, and the example I gave earlier was if your grade was an A or if your grade was a B, the probability of A or B occurring is simply just the probability of you getting an A, and then we're going to add the probability of you getting a B. We simply just add those two events together. So if you have a 10% chance of getting an A and a 20% chance of getting a B, then you have a 30% chance of getting an A or a B. However, if they're not mutually exclusive, then the equation does change slightly. If they're not mutually exclusive, we have to use what's called the general rule. And the general rule says if we want to OR two events together, we still add them independently just like we did up here. However, we have to subtract out the probability of E and F occurring at the same time. And this is easier to understand when I draw the picture. Okay? So for example, the example I gave earlier was you could be in a statistics class, or you could be in an advanced physiology class, or you could be in both classes, right? So if I wanted to find the probability of you being in a stat class or you being in physiology class, then we simply just add the two separate. So the probability that you're in stats, and then we're going to add the probability that you're in physiology. I'm going to highlight that in red. But now what you see what we've done is when we added these two probabilities separately, what happened is we added this middle section twice. We added all of these people once when we took all of the statistics students, but we also added it a second time when we added all the physiology students because those students happen to be in the middle and were added twice because they were in both classes. So to counteract that or to fix that, we have to subtract the probability of being in stats and physiology at the same time. So the upside down U represents and. So we subtract that portion back out because it's been added twice. We did not have to do that over here because they didn't have anybody in common. So we could just add the two independently. But if they are joined and you can't add the middle part twice, you would end up with too big of a probability. And last is called the complement rule. The complement rule says if E represents any event, then E to the power C, it's called the complement of C, represents the complement of E, then the probability of the complement equals 1 minus the probability of the event occurring. Okay, so let's do an example here. If this is an event E, then this is the probability on the outside that represents the complement of E, or it's in other words the probability it will not occur. So complement actually is another word for opposite. So an example of that would be if here is the probability it will rain today, let's call it 30% chance. Then out here is the probability it will not rain today. So if the probability it will rain is 30%, the probability it will not rain everything outside is going to be 70. In other words, everything inside plus everything outside is going to add up to 100%. So we would say over here that the probability of it not raining is simply just going to be 1 minus the probability that it will rain, because they add up to 100%.